What if I told you that an AI system designed to predict, say, tomorrow's stock price, might not actually look at yesterday's stock price at all?
Right, which sounds completely backwards when you first hear it.
Exactly. What if instead the algorithm only looks at the mathematical mistakes it made yesterday, like using its own past errors as the sole fuel to predict the future?
It is a wild concept, honestly.
It really is. It sounds almost like, I don't know, trying to drive a car by only looking at the skid marks you left behind.
That's a great way to put it.
But that specific mechanism is actually a cornerstone of modern predictive modeling. Welcome to the deep dive, everyone. Today, we are taking on the role of your co-instructors to unpack the engine that drives the entire artificial intelligence revolution.
Yeah, we are talking about machine learning.
We are drawing from the core concepts of the ISA Artificial Intelligence Primer, specifically Chapter 3, but we are leaving the intimidating jargon at the door.
Because the stakes for understanding these mechanisms are just, well, they're higher than ever right now.
Sure.
Machine learning is no longer just this isolated discipline reserved for, data scientists or software engineers locked in some freezing server room.
Right. It's everywhere.
It is the fundamental literacy required for anyone interacting with modern technology or business operations or digital infrastructure. I mean, if you don't grasp how the machine actually learns, you are entirely blind to how it reaches its conclusions.
You don't know how it handles complex inputs or, and this is key, where its mathematical blind spots actually are.
Exactly.
So we are going to build your mental model from the ground up today. We will start with the foundational math that allows a machine to literally experience data.
Which is a cool concept in itself.
Totally. Then we'll roll up our sleeves and get into the really unglamorous reality of data preparation because, let me tell you, raw data is inherently chaotic.
It's a mess.
A total mess. And from there, we are going to tear down the three major paradigms of machine learning: supervised, unsupervised, and reinforcement learning.
We'll explore the mechanisms, the math, and the underlying logic for all of them.
So let's just unpack this. The logical starting point is defining the core differentiator, right? Like what actually separates a machine learning model from traditional, highly complex computer programming.
The real paradigm shift there is the move from explicit rule-based programming to experiential learning.
Okay, break that down for us.
So in a traditional software environment, a human programmer sits down and writes highly specific, exhaustive conditional statements, like if variable A exceeds threshold B, then execute function C.
Right, so the human is accounting for all the logic.
Precisely. The human maps it all out. Machine learning, as a subfield of AI, just completely discards those manual rules.
It throws them out.
Yeah. Instead, it provides the machine with an overarching algorithmic architecture and just feeds it data. It allows the system to identify the hidden relationships and essentially define the rules for itself.
So rather than handing the computer a map of the maze, you basically drop it in the maze with a mathematical compass and just let it build its own map.
That's a perfect analogy.
But the primer heavily emphasizes the underlying math here. Like, it mentions statistics, linear algebra, calculus, and optimization.
Yes, the big ones.
And when we talk about this math, I mean, we aren't talking about a machine sitting there solving equations for a high school grade, right?
No, definitely not.
It feels more like the math is the physical law of the machine's universe. Like it provides a sensory system for the algorithm to adjust its own internal recipe.
That concept of a sensory system is highly accurate, actually. Because when you feed a massive data set into an algorithm, the linear algebra kicks in to structure that information.
Okay.
It maps the data points into an n-dimensional space using matrices and vectors. And then the system uses probability and statistics to sort of weigh the relationships within that space.
But the actual learning mechanism, like the way the recipe improves over time, that relies heavily on calculus and optimization, doesn't it?
It does, because calculus measures the rate of change. So if the machine makes a prediction, and that prediction is wrong, it uses calculus to figure out exactly how to tweak its internal weights to be slightly less wrong the next time.
Which is where gradient descent comes in, right?
Exactly. We can look at this through the lens of gradient descent. Imagine the machine's error rate is a physical landscape, like a landscape of hills and valleys.
Okay, I'm picturing it.
The goal of the learning process is to find the lowest possible point in the deepest valley, because that represents the lowest possible error.
Right, you want the error to be at the absolute bottom.
Right. So calculus allows the machine to calculate the gradient, or the slope, of the curve at its current position. By taking the derivative of its error function, The machine knows exactly which mathematical direction is downhill.
Oh, wow.
Yeah, and then it updates its parameters to take a step in that downhill direction.
So it's essentially feeling its way down the mountain in the dark, step by step, until it hits the bottom.
That's exactly what it's doing.
But before a machine can start navigating that mathematical landscape, it needs a stable terrain. And that requires data.
A lot of data.
And raw data is chaotic. It's inconsistent, and often it's highly skewed. Like if we just dump raw server logs or, scraping outputs into our gradient descent engine, we are going to get terrible results.
Oh, absolutely. The industry saying garbage in, garbage out exists for a very good reason.
So we have to talk about the preparation phase. This is section 3.2 in the primer.
Right, the kitchen prep.
This is arguably where data scientists spend the majority of their time, isn't it?
Oh, by far. The pipeline involves rigorous cleaning, scaling, and transformation. You have to handle missing values, smooth out noisy data fit.
Because if you don't remove outliers, they would artificially pull the algorithm slope in the wrong direction.
Exactly. They'd throw off the whole gradient. But the mathematical scaling is where it gets really interesting to me.
Give us an example.
Take a data set analyzing real estate. You might have one feature representing the number of bedrooms, which ranges from, say, 1 to 5. And another feature represents the square footage, ranging from maybe 1,000 to 5,000.
Oh, I see where this is going. If we just feed those raw numbers into a linear algorithm, the math is going to see the number 5,000 and naturally assume the square footage is 1,000 times more statistically significant than the number of bedrooms.
Purely based on the magnitude of the integer.
Right, which is completely false. A 4-bedroom house is a huge deal, even if the number 4 is tiny compared to 2,000 square feet.
Which necessitates standardization or normalization.
So you have to translate them.
Yeah, the data must be mathematically transformed. Often it's centered around a mean of 0 with a standard deviation of 1 so that all features operate on a level playing field.
Because the algorithm needs to evaluate the actual relationships between the features, not just be blinded by their raw numerical scales.
Exactly. And we also run into the problem of categorical data.
Oh, right, like words.
Right. If a data set have a column for product color with options like red, green, and blue, an algorithm cannot perform calculus on a word.
It just doesn't compute.
Right. So a novice approach might be to just assign them numbers, like red is 1, green is 2, blue is 3.
But wait, that introduces a massive mathematical flaw, doesn't it?
It does.
Because the algorithm will look at those integers and assume that blue, which is 3, is somehow 3 times as much as red, which is 1.
That is a critical trap, yes.
Yeah.
And it is exactly why feature engineering requires techniques like one-hot encoding.
One-hot encoding? How does that work?
Instead of using one column with values 1, 2, and 3, the engineer transforms that single color feature into 3 separate binary columns.
Okay.
So you get is red, is green, and is blue. And the values in those new columns are only ever 0 or 1.
Oh, that's brilliant. So it's basically a simple yes or no for each color.
Exactly. You preserve all the categorical information without tricking the linear algebra into seeing false mathematical magnitudes.
That makes total sense. And beyond just the shape of the data, we also have to deal with the distribution of the data, right?
Yes, the imbalance problem.
The primer places heavy emphasis on handling imbalanced data sets, because this is where the algorithm's learning process can be fundamentally corrupted.
It really can.
Let's say you are building an AI to detect fraudulent transactions on a huge credit card network. In a data set of 1 million transactions, perhaps only 100 are actually fraud.
Right, so the normal transactions completely eclipse the minority class.
If you train a model on that raw distribution, what happens?
The algorithm will quickly optimize for the easiest path to a low error rate. It's doing gradient descent, remember. So it will realize that if it simply predicts not fraud for every single transaction, it will achieve a 99.99% accuracy rate.
Wow. Because almost none of them are fraud.
Right. So on paper, it looks highly successful. The boss sees 99.99% and is thrilled. But in reality, it has failed completely at its intended function.
It hasn't learned to detect fraud at all. It has just learned a mathematically lazy view of the world.
Exactly. So we have to manipulate the distribution before the training even begins.
And the primer mentions 2 specific opposing mechanisms for this, Semote and Temecklings. Let's break down how these actually function under the hood, starting with Semote, which stands for Synthetic Minority Oversampling Technique.
Right.
How does Semote mathematically invent new fraud cases without just blindly duplicating the existing ones?
Well, blind duplication doesn't add any new informational variance for the model to learn from, so that wouldn't help much.
It's just showing it the exact same picture twice.
Right. So SMOGA operates by interpolating between existing minority data points. It takes a known fraud case, looks at its nearest neighbors in that n-dimensional feature space we talked about, and literally draws mathematical lines between them.
Okay, I'm visualizing these lines connecting the rare fraud points.
And then it generates brand new synthetic data points at random intervals along those lines.
Oh, wow.
Yeah, it creates realistic, distinct variations of fraud that help the algorithm understand the broader shape of the minority class.
So it's synthesizing realistic practice data. That's incredibly smart.
It's very effective.
But then Atomic Links approaches the imbalance from the completely opposite direction, right? It's an undersampling technique.
Yes, it focuses on the boundaries. Atomic Links addresses the ambiguity where the majority and minority classes overlap.
Because that overlap is confusing for the AI.
Exactly. It scans the dataset to find pairs of data points, one normal transaction, one a fraudulent transaction, that are incredibly close to each other in the feature space.
Like almost identical transactions, but one is fraud and one isn't?
Right. These borderline cases confuse the algorithm's calculus. Atomic Link identifies that extreme proximity and typically deletes the data point belonging to the majority class.
By systematically removing those overlapping majority points, it basically carves out a sort of mathematical moat between the two classes,
A moat is a great analogy. It makes the boundary sharp and distinct.
making the gradient much easier for the algorithm to calculate. Okay, so we've cleaned the data, we've scaled it, we've one-hot encoded the categories, and we balanced the classes with SME and Atomic Links. The dataset is pristine.
It's ready to go.
But wait, we still can't just feed the entire thing into the model, right? The primer is very strict about this. We have to partition it, adhering to the 7 in 2010 rule.
The partitioning workflow is completely non-negotiable if you want a model that actually performs in the real world.
Walk us through it.
You take your pristine data set and lock away 20 to 30% of it in a vault. That is your testing set. The algorithm must never, ever see or interact with this data during the training
You're
process.
totally quarantined.
Completely. The remaining 70 to 80% is then split again, usually into an 80-20 ratio, creating your training set and your validation set.
Let's explore the necessity of that middle bucket, the validation set, because I think I understand the training set. That's like the textbook the model reads to learn the patterns, right?
Right.
And the testing set locked in the vault is the final exam. But why do we need the validation set acting as a practice quiz? What specific mechanism are we trying to prevent here?
We're trying to mitigate the bias variance trade-off. Specifically, we're trying to prevent a state known as overfitting.
Overfitting? What does that look like?
If a model only interacts with the training set, it can become too complex. It stops learning the underlying general patterns and starts memorizing the specific noise and anomalies of that exact data set.
Ah, so it essentially memorizes the textbook word for word, but fails to grasp the broader concepts.
Exactly. If you give it a real-world problem, it fails because it's only good at answering the exact questions from the textbook.
So during the training loop, the engineers periodically pause the process and test the model against the validation set.
Yes. And because the model isn't using the validation data to adjust its internal weights, it provides an honest metric of how well the model is generalizing.
I see.
Building on that, the validation set is actively used by the human engineers to tune the model's hyperparameters.
Hyperparameters, those are different from regular parameters.
Right. Think of hyperparameters as the overarching settings of the algorithm itself. Things like the learning rate, which dictates how large of a step the algorithm takes down that gradient descent mountain we talked about earlier.
Oh, so the humans adjust the hyperparameters based on the validation performance until the model is stable.
Exactly. And only then, when the architecture is totally finalized, do you open the vault and run the testing set to get your final unbiased performance metric.
It enforces strict data hygiene. It prevents data leakage.
Crucial stuff.
Okay, now that our data is prepped and partitioned, we can finally explore the major paradigms of how the machine actually processes it. This brings us to section 3.3, supervised machine learning.
The guided path.
Exactly. The defining characteristic here is that the algorithm is given a target. It is actively mapping independent variables, the predictors, to a specific dependent variable, the outcome.
And regression algorithms are the bedrock of supervised learning here. They're designed to model the relationship between those independent variables and a continuous target variable.
By continuous, you mean a numerical value that can scale indefinitely, right? Like predicting revenue or temperature.
Yes. And linear regression is the most fundamental of these. It attempts to draw a straight line of best fit through the multi-dimensional data space using ordinary least squares.
Just trying to minimize the distance between the prediction line and the actual data points.
Exactly. But the primer introduces a suite of advanced regression techniques designed to handle high-dimensional complexity. We're talking about lasso, ridge, and elastic net.
And these aren't just drawing a simple line, right? They are actively penalizing the model. How do these regularization mechanisms actually work?
Well, regularization is basically a mathematical safety valve against the overfitting we just discussed.
Okay.
If a model is given hundreds of features, a standard linear regression might assign complex weights to every single feature just to perfectly touch every single training data point.
Which results in a chaotic, overly complex model that won't generalize.
Right. So ridge regression applies what's called an L2 penalty. It adds a mathematical cost to the algorithm's loss function based on the squared magnitude of the coefficients.
So it basically pulls all the feature weights closer to zero, keeping them small and stable.
Exactly. Ridge dampens the noise.
Yeah.
But lasso regression uses an L1 penalty, which behaves very differently.
How so?
Instead of squaring the magnitude, it takes the absolute value. And the mechanical result of that L1 penalty is that it can force the coefficients of less important features all the way down to absolute zero.
Wait, really? Absolute zero?
Yes.
So lasso acts as an automatic feature selector.
That is the critical distinction, yes. If you feed it a data set with 50 variables, the L1 penalty might determine that 30 of them are essentially just noise.
And it reduces their impact to zero, dropping them from the equation entirely.
Exactly. It prunes the model.
That is fascinating. It's a self-pruning mechanism built right into the calculus. And then I assume elastic net is a combination.
You got it. As the name suggests, ElasticNet strategically combines the L1 and L2 penalties. It brings the feature selection of lasso and the stability of ridge into a single algorithmic approach.
Best of both worlds. Now, within supervised learning, we also have to deal with time-dependent data, time series. And this brings us back to the hook we opened the whole deep dive with.
Yes, the stock market example.
Right. When modeling time series data, the assumption is usually autoregressive. Like if a stock was at 10, then 12, then 14, the model looks at those past outputs to predict it'll hit 16.
Which is intuitive for humans.
Extremely intuitive. But the primer highlights moving average, or MA models, which operate on a totally different philosophy.
Right. Moving average models completely discard the assumption that past outputs are the best predictor of future outputs.
So what do they look at?
Instead, an MA model focuses entirely on past errors. Statisticians call them random shocks.
Random shocks.
Yeah. In many systems, there is a stable underlying mean, but the actual observed values are constantly buffeted by unpredictable random events.
So the MA model is essentially tracking the turbulence.
Exactly. It calculates the difference between what was expected yesterday and what actually happened. That's the error term. It then uses a weighted linear combination of those past random errors to adjust the prediction for tomorrow.
It assumes that the ripple effects of past mistakes are the most accurate way to model the immediate future deviation from the mean.
Right. It is a brilliant approach for highly volatile environments where sudden random fluctuations dictate the short-term movement more than the historical baseline does.
Supervised learning, whether it is using lasso to prune features or MA models to track random shocks, is highly structured. You have a target. You are guiding the algorithm.
It's very intentional.
But when we transition to the second major paradigm, unsupervised machine learning section 3.4, that structure completely vanishes.
That's the Wild West.
Exactly. We are dealing with raw, unlabeled data. There is no dependent variable. The algorithm's only directive is to explore the void and find the hidden architecture within the dataset.
It is purely exploratory. And the most ubiquitous unsupervised technique is clustering,
Which is segmenting a vast, unorganized data set into coherent subgroups based on mathematical similarities.
Right. Yes. And the primer explicitly differentiates between hard clustering and soft clustering.
What's the difference?
Hard clustering is absolute. A data point is assigned definitively to cluster A or cluster B. There's no middle ground.
But soft clustering is more nuanced.
Exactly. Utilizing algorithms like fuzzy C-means, soft clustering acknowledges the reality of ambiguous data.
So a point resting on the boundary isn't forced into a binary choice. The algorithm calculates a probability distribution.
Right. It might state that a data point has a 92% probability of belonging to cluster A and an 8% probability of belonging to cluster B.
I love that. It preserves the nuance of the overlapping boundaries.
And regarding the methodology of actually forming these clusters, agglomerative hierarchical clustering is a really fascinating mechanical process.
Agglomerative, that's a mouthful. How does it work?
It is a bottom-up approach. Imagine a massive data set with 10,000 distinct points. In the first step of the agglomerative process, the algorithm assigns every single point to its own individual cluster.
So you start with 10,000 tiny, distinct clusters.
Exactly. Then it begins calculating the distance matrix. It scans the entire n-dimensional space to find the 2 points that have the shortest Euclidean distance between them.
The 2 closest points.
Right, and it fuses them together.
Okay, so now you have 9,999 clusters.
Precisely. And then the algorithm iterates. It recalculates the distance matrix, perhaps using something like Ward's method to minimize the variance within the newly formed clusters and merges the next closest pair.
And it just keeps going.
It continues this systematic fusion until every single data point has been agglomerated into one massive singular cluster.
But wait, if the final output is just one giant cluster that contains everything, isn't the analysis completely useless?
But the power of the agglomerative approach isn't the final giant cluster. It's the visual record it creates along the way.
The dendrogram.
Yes, the dendrogram. It is a tree-like diagram that plots the entire history of the fusions. The vertical axis represents the mathematical distance at which the clusters merged.
Oh, I see.
So by examining the dendrogram, a data scientist can visually identify the natural joints in the data. They can take a metaphorical pair of scissors and cut the tree horizontally at whatever distance threshold yields the optimal number of distinct clusters for their specific business problem.
That's amazing. You build it all the way up just so you can precisely prune it down.
Exactly.
And speaking of bottom-up pruning, the unsupervised paradigm also tackles association rules. This is the domain of market basket analysis, right? Finding the hidden if-then relationships in transactional data.
Yes, the famous retail examples.
Like if a customer buys diapers, what is the probability they also buy baby wipes? Or surprisingly, beer?
Right, the diaper and beer correlation is a classic. But the mathematical challenge here is combinatorial explosion.
Combinatorial explosion, meaning too many combinations to calculate.
Exactly. If you have a supermarket inventory with 50,000 unique items, evaluating every single possible combination of items to find frequent relationships requires astronomical computational power.
It would take forever.
It would. This is where the a priori algorithm provides an elegant solution through systematic pruning.
A priori operates on a really clever core principle, doesn't it? Like, if an item set is infrequent, all of its supersets must also be infrequent.
That is the exact mechanism. A priori calculates the support metric, which is the baseline frequency of an item appearing in the dataset.
Okay.
It starts at the bottom, looking only at single items. If it discovers that, say, purple shoelaces appear in only 0.001% of all transactions, it falls below the minimum support threshold.
And because purple shoelaces are incredibly rare on their own, the algorithm mathematically guarantees that purple shoelaces and a toaster must be even rarer.
Exactly.
So a priori instantly prunes that entire branch of combinations. It flat out refuses to calculate the larger item sets if the foundational subset is weak.
It dramatically slashes the required computational load by ignoring these statistically impossible combinations.
It's so efficient. Now, beyond organizing data and finding associations, unsupervised learning is crucial for data simplification, right?
Absolutely. High-dimensional data is a massive bottleneck in machine learning.
Because if you have a data set with 1,000 distinct features, the mathematical space becomes so vast and sparse that algorithms just struggle to find meaningful proximity.
We call that the curse of dimensionality. And it necessitates dimensionality reduction. Principal component analysis, or PCA, is the foundational technique here.
Let's visualize how PCA actually compresses the data without just blindly deleting columns.
Okay.
If we go back to our real estate data set, we might have columns for square footage, number of bedrooms, lot size, and number of bathrooms. To a human, it's obvious that these features are highly correlated.
Right. A house with massive square footage almost certainly has more bedrooms and bathrooms.
They are mathematically overlapping.
And PCA leverages that correlation. It calculates the covariance matrix of the entire data set and extracts the eigenvectors and eigenvalues.
Whoa, eigenvector.
I know, it sounds intense. But essentially, it just rotates the multidimensional axis of the data to find the directions where the data varies the most.
Okay, that makes sense.
It takes those highly correlated housing features and synthesizes them into a brand new abstract variable called a principal component.
So principal component 1, or PC1, isn't explicitly square footage anymore. It's a mathematically derived vector that captures the overall size and scale of the property, absorbing the variance of 4 or 5 original columns into a single dimension.
Exactly. And PC2 might capture a different variance, like age and condition.
So you reduce 1,000 noisy, overlapping features down to 20 highly dense, independent principal components.
Preserving the essential narrative of the data while exponentially speeding up the computation.
It is a masterful compression of the mathematical space. Which brings us to the final and arguably most complex paradigm in the syllabus. Section 3.5, Reinforcement Learning.
The trial and error phase.
Yes, reinforcement learning discards the continuous target variables of supervised learning, and it moves beyond the static exploration of unsupervised learning. It is a highly dynamic behavioral process.
It operates fundamentally like an agent navigating a video game environment.
Right. And the primer formalizes this through the Markov agent-environment interaction loop. We really need to clearly define the architecture of this loop because it is the engine for everything that follows.
So, the Markov loop requires an agent, an environment, a state, and a reward.
4 parts.
Yes. The agent is the decision-making algorithm. The environment is the bounded world it operates within. The state is a mathematical representation of the current conditions of that environment at a specific moment in time.
Let's map this to a game of chess to make it concrete.
Perfect.
The agent is the algorithm controlling the white pieces. The environment is the rules and geometry of the 64-square board. And the state is the exact coordinate location of every single piece on the board at, say, turn 12.
Correct. The loop initiates when the agent observes that state and selects an action from its available options.
Like moving a knight.
Right. It executes the action, which fundamentally alters the environment. The environment transitions to a new state, and it sends a reward signal back to the agent.
So a positive reward for capturing a piece, and maybe a negative reward for exposing the king.
Exactly. The agent updates its internal policy based on that reward, and the loop fires again.
But this continuous loop creates the fundamental tension of reinforcement learning, the exploration versus exploitation trade-off.
This is a brilliant algorithmic dilemma.
Because if the agent finds a specific sequence of actions that yields a reliable, moderate reward, its mathematical impulse is to exploit that sequence continuously to maximize its score, right?
That is the trap of the local optimum. If the algorithm uses a pure greedy strategy, always taking the action with the highest immediate known reward, it will never risk exploring unknown states.
Why is that bad?
Because hidden in those unknown states might be a sequence of actions that yields a massively higher global optimal, a huge payout that it just never finds because it's playing it safe.
So engineers implement strategies like epsilon greedy to force the algorithm to take risks.
Yes. Most of the time, the agent exploits its knowledge. But a small percentage of the time, the epsilon value the agent is mathematically forced to choose a completely random action.
Regardless of the expected reward.
Purely to explore the map.
That's so cool. And to make the AI actually care about the long-term discoveries it makes during exploration, we have to introduce the concept of discounted reward.
Section 3.5.6.
The algorithm needs a mechanism to value a reward that is 10 steps away. It uses the Bellman equation, which incorporates a discount factor, usually denoted by the Greek letter gamma.
Right, and gamma is crucial. If gamma is set to 0, the AI acts like a goldfish.
A goldfish?
Yeah, it only cares about the immediate reward of the very next step.
Yeah.
It has no long-term memory or planning.
But if gamma is closer to 1...
Then the AI becomes a visionary.
Yeah.
It calculates the value of a current state, not just by what it gets right now, but by the entire chain of future rewards that state makes possible.
It literally learns delayed gratification.
Exactly. To contextualize these expected total discounted rewards, what we call Q values, the text relies on a classic MIT deep learning experiment utilizing the Atari game Breakout.
Oh, I love this example. Let's visualize the Breakout environment for everyone.
Go for it.
You have a paddle at the bottom of the screen, moving left and right to bounce a ball upwards into layers of colored bricks. If the ball drops past the paddle, you lose. The agent controls the paddle, optimizing for the reward of breaking bricks.
Now, the MIT experiment analyzed 2 specific state action pairs in this game.
Okay.
In pair A, the ball is falling straight down, and the paddle is positioned directly underneath it. The action chosen is to hit the ball dead center, sending it vertically.
Simple enough.
In pair B, the ball is falling at an angle, and the action chosen is to strike it with the very edge of the paddle, forcing a sharp deflection.
To a novice human player, hitting it dead center in pair A feels secure, You guarantee the immediate survival of the ball.
Right. But the Q value, the expected future reward calculated by the Bellman equation, is actually much higher for pair B.
Why?
Well, the mechanism of the game's physics dictates that hitting the ball vertically in pair A will break a single brick, and the ball will fall straight back down.
Yeah.
Minimal reward, high required maintenance.
You have to keep hitting it over and over.
Exactly. But striking it at a sharp angle in pair B sends the ball bouncing laterally. It ricochets off a brick, off the side wall, and potentially gets trapped in the ceiling above the brick layers.
Oh, it bounces wildly back and forth across the ceiling, taking out 15 bricks in a single chaotic flight before it ever returns to the paddle.
Exactly. The reinforcement learning agent, tracking the discounted future rewards, discovers that engineering those chaotic ricochets yields a vastly superior cumulative return.
It learns an advanced strategy that humans intuitively grasp, but it does so entirely through the mathematical optimization of Q values.
It's beautiful. However, calculating the exact Q value for every single possible pixel configuration in a video game is computationally impossible.
Right, a standard table cannot hold that many states. Every pixel change is a new state.
Which necessitates the evolution into deep Q networks, or DQNs.
A DQN replaces the massive lookup table with a deep neural network.
Yes. You feed the raw pixel data of the Atari screen into the neural network, and it processes the visual patterns to output the estimated Q values for moving left, moving right, or staying still.
But training a neural network on a continuous stream of highly correlated video game frames is notoriously unstable, isn't it?
Extremely unstable. If the agent makes a mistake and falls into a negative feedback loop, the neural network can catastrophically forget everything it has learned.
Which is why the architecture requires advanced stabilization techniques. The primer specifically mentions experience replay and target networks.
Let's start with experience replay. In a standard learning loop, the data is highly sequential. Frame 2 is almost identical to frame 1.
Right.
If you train the network on that sequential data, it overfits to the immediate moment. Experience replay breaks that temporal correlation.
By building a massive memory buffer.
Yes. The agent stores millions of past interactions, the state, the action, the reward, and the resulting state.
So during the training cycle, the algorithm doesn't just look at the immediate frame. It reaches into the memory buffer and pulls a randomized batch of past experiences.
I like to think of it like the AI is sitting in the locker room, dreaming about randomized moments from thousands of past games.
Allowing the neural network to learn from a diverse, uncorrelated data set.
It solidifies the foundational mechanics without over-indexing on whatever the current sequence is.
And the second stabilization technique, the target network, addresses the shifting goalposts, right?
Exactly. If you use a single neural network to both select your actions and estimate the future Q value targets you are aiming for, the math becomes highly recursive and unstable.
It's like trying to calibrate a sniper rifle while you are running a full sprint. The target is moving relative to your own erratic motion.
Precisely. Or rather, the mathematical equivalent is divergent oscillations.
How do they solve it?
Engineers clone the network. The active network makes the decisions and updates its weights continuously. But the target network, which is used strictly to calculate the expected future rewards, is kept frozen.
It provides a stable, stationary mathematical target for the active network to learn against.
Right. The target network is only updating with the active network's weights periodically. It brings controlled, stepped stability to the highly volatile reinforcement environment.
That is incredible. And with that, we have literally traversed the entirety of the Chapter 3 syllabus architecture.
We covered a lot of ground.
We really did. From the foundational matrices of linear algebra through the rigorous cleaning and validation pipelines, we've watched lasso regression prune our supervised datasets, and we've seen agglomerative clustering build dendrograms out of the chaotic, unsupervised void.
And finally, we track the Q values of a neural network dreaming of past Atari games just to stabilize its own reinforcement loop.
We have completely unpacked the mechanics of the machine learning engine.
We have covered the fundamental physics of the AI revolution. But, as we conclude our analysis of how the machine learns, how it balances immediate exploitation with long-term exploration, and how it uses a discount factor to value future states, I think there is a profound secondary application of these concepts.
So I have a feeling we are going to pivot from artificial intelligence to biological intelligence.
I think we have to. Consider the architecture of human habit and human decision-making for a second.
Okay,
How much of our daily lives is governed by a biological approximation of a deep Q network?
that's a deep thought.
When we structure our routines, when we decide whether to exploit a known, comfortable career path or explore an unknown, risky opportunity, are we properly tuning our own epsilon greedy algorithms?
Are we forcing ourselves to take that random exploratory step?
Exactly. And, more importantly, when we make choices today, are we accurately calculating the discounted rewards of our future states, or are we just stuck in the local optimum of immediate gratification?
We act like gamma is 0.
We do. It is a fascinating mathematical lens through which to view our own human agency. Definitely something for you to explore on your own.
That is the ultimate question to walk away with today. Are you engineering the ricochets of your own future, or just bouncing the ball straight back down?
Well said.
Thank you all for joining us as we deconstruct the engine of the future. We'll catch you on the next deep dive.